Okay, we are now recording. So this week we'll be reading this paper called MoAI, Mixture of All Intelligence for Large Language and Vision Models. So sometime back we covered mixture of MOE models, mixture of expert models, especially I think we covered Mistral, and um, these the MOE models have very good advantages. First, they can give really good results even with fewer with lesser inference time even. Yeah. And my initial perception was that in mixture of experts there'll be the gating mechanism is supposed to happen at the uh, yeah, at the base of all the layers, encoder or decoder layers. But to my surprise, it happens in each and every feed forward layer in the attention block. So continuing from there, the idea behind mixture of experts is like like a specific part of the model will be better at certain types of tasks, and that happens at training time, and it is trained via a gating mechanism. In a gating mechanism, what happens is, let's say you have 8 experts, then at most you will select the results from 2 experts, and the results from these 2 experts is further propagated to the next layers that are above the current on, attention block. So yeah, so this is our starting point, mixture of experts. So now, yeah.
Sorry, go ahead.
Yeah. So now the idea is the you can further extrapolate this idea of having different sort of experts within your model. So till now, what has happened is like we have seen models which are either language based or multimodal language models, which are combining, which are having these experts, but they are only in one particular domain. So now the idea is, let's say if we have one such part of our model, right, which is, let's say, just a language model or a multimodal language model, can we bring in experts which are from the same domain, but are, but yeah, can we inculcate their results into our training? So the idea behind this paper is that they are leveraging external vision models, because a lot of research has been already done in the area of computer vision in the past decade, and the idea is how can we leverage that sort of expertise in our own in the models that we can build through these mixture of experts and through instruction fine tuning. How can we leverage their results into our models? And this opens up a very nice and interesting idea that we can combine many more models into one single model to do specific or many different types of tasks. And the models, the results that they have shown in this paper, they are very good zero shot results also they are getting. So that is the idea behind covering this paper. So let's start. um, so yeah, so LLVMs are basically large language and vision models, and these current large language vision models have disregarded the detailed and comprehensive real-world scene understanding available from specialized computer vision models, especially visual perception tasks like segmentation, detection, scene graph generation, and optical character generation. So the idea is that these LLVMs, they basically they get better performance based on their capacity. Basically, if you increase the number of layers that is there in the, not just in LLVMs, in LLMs also, if you increase the number of layers, if you increase the size of the hidden dimension, their capabilities come from the number of parameters that you can increase in the model. But the idea is, can we keep the number of trainable parameters low and at the same time use all the existing models which are there already for scene graph generation, segmentation, and OCR. So that is the idea behind this paper. And the two main contribution of this paper are these two models. One part is called the MoI compressor, which basically compresses all the understanding that you can get about a visual scene from the OCR model, segmentation model, panoptic segmentation, and other such models. And MoI mixer is basically, now that you have this information from these visual models, how do you integrate them in a MLM model, which is multimodal language model, and how can you combine them together so that they work together nicely. So yeah. So again, as I was saying earlier, that the majority of performance that people have noticed in LLVMs or even in LLMs is comes by increasing their size. And when they increase the size of the model, the zero-shot performance of the model also increases. And they argue that the fundamental scene perception ability in humans also may stem from various cognitive functions, including recognizing object presence, determining their positions, identifying their states, understanding their relationships, and extracting spatial scenes layout. So basically, what they're trying to mimic here is like you can have one particular smaller model which is really good at something. For example, let's say if we are talking about just NLP, let's say we have a very good model which does NER really nicely. Another model does translation very nicely. Right now, what everyone is doing is they are increasing the model capacity in such a way that the model does NER and translation by itself, it is able to do it much more better because you are throwing a lot of data and you are increasing the model size. However, what about if we can take these smaller models and combine them into transformer architecture in such a way that we can leverage their understanding and we can get uh, similar results in in a less number of training parameters. And yeah, so the authors are trying to shift the focus from instruction tuning to utilize these external CV models to enhance the real world scene understandings of LLVMs. And yeah, so they have basically introduced a new large language vision model, which is a mixture of all intelligence. That's the name they have given, which leverages auxiliary visual information obtained from various sources. So they have covered four major CV models. One model does panoptic segmentation, which is basically trying to understand what objects are there in the foreground and in the background. The second one is open world object detection, which is what all objects are present in a particular image. Scene graph generation, which is SGG, and OCR, optical character recognition. And they introduced two new modules. One is called MoAI compressor and MoAI mixer. MoI compressor aligns and condenses the verbalized outputs of the external CV models into auxiliary visual information. And MoAI mixer blends three types of intelligence: visual features, auxiliary features from the external CV models, and language features into a cohesive whole. So traditional LLVM models, they work on two sort of features. Since it's a multimodal model, it works both, it takes input of both the image information and the language information. So what these guys have done is added these auxiliary features from external CV models, and that is the whole idea behind this paper. So they are suggesting that by combining the MoAI compressor and MoAI mixer, their model is effectively utilizing outputs from external CV models and mix these three sources of intelligence. So these The sources of intelligence they are referring are the image features, visual features, the language features, and the external features that are there that they have got from these pre-trained, very specific vision models. And you can easily extrapolate this idea to a whole lot of things. Like if imagine if you can add your pre-trained models for very specific tasks and purposes to your these bigger LLMs, and that could be really interesting to see in the future. And they suggest that their model has significantly outperformed in visual perception scores. Uh, Three strong LLVM baselines of InstructBlip, QuenVL, and Lava 1.5. And they also share that their model has very good zero shot performances. So before we start related works, any questions till now? Okay.
I think we're good for now. Yeah, good.
Sorry.
I said I think I'm good for now. Um,
Okay.
yeah.
Okay. So yeah, let's continue with
I mean,
the.
one question, I don't know if you covered this. Does it say all the different models that they use? Is it easily interchangeable with whatever you want?
They did not mention if they are easily interchangeable, but they have mentioned what all models they have used exactly for integrating these auxiliary visual features. They have mentioned that. We'll cover that.
Okay, got it. Um, yeah. Is like the vision models different than the language ones? Because I feel like in language, I haven't seen someone do this, right? Like I guess Mistral, but they trained all of they don't like necessarily combine GPT with like, I don't know, 5 other types of LLMs. Is this different in vision that makes this useful?
I mean, the idea is that if you try to, uh, add a Mistral model to a GPT model, you are basically taking an LLM and adding it to an LLM, right? That sort of goes into the territory of merge kit library that I think we discussed sometime.
Yeah, exactly. Is this similar to that?
No, this is basically different because here you are taking models which are very specific and they like a model for let's say OCR, right? Is won't be able to do any task that a traditional LLVM is doing because their job is literally different. They are trying to identify characters in an image. So the idea is like how can you integrate these models which are like in sort of a different domain, like it's not exactly doing the job of an LLVM, and how can we leverage their expertise in improving the performance of LLVMs? So
Okay.
it would be something like if you can add, let's say, Spacey model to Mistral. Uh, think of, I mean, it's not the perfect example, but let's say getting some capabilities from Spacey and integrating their capability into Mistral. It is something like that.
Okay, yeah, fair enough.
Yeah.
I wonder if
So
anyone has tried the merge kit approach for vision models though. Like I feel like it should work on anything. I
yeah,
haven't seen anyone do it, but like literally all that's doing is randomly combining the weights in various ways, right? Like I don't see there's any
yeah.
reason that can't happen for vision models too.
Yeah, I mean that's my perception also, but I have not uh, went in deep into it, like how is it doing all that. But
Merge kit.
yeah, merge kit. Yeah, I have not like merged any model
Yeah.
till
I
now.
mean, I feel like just merging it's not going to give you too much insight because like as you said, right? It's just kind of YAML files that you run and get an output. But yeah, they do have papers. We covered it very briefly, but yeah, maybe we can just try. I don't know. It shouldn't be too hard to try. They just allow you to define the like Hugging Face model, specify some parameters around which layers you want to merge and so forth, and then I mean, it might not be too hard to try,
Yeah,
just out of curiosity. Okay, anyway, go ahead, go ahead.
yeah, we can definitely try that. Because I am really inclined towards exploring this MOE approach for some time. Uh, like, I think there is first, if we could cover, MOE papers a lot more, then we can definitely go to market also, because they are like sort of related, not related, but um, yeah, I think they both can be leveraged together. Anyways, so continuing on the related works. So as we discussed earlier, that LLMs demonstrate strong zero-shot or few-shot performance across various language tasks, and these zero-shot and few-shot performances, they go up as we increase the model size and the data that we train them on. And after these construction of these LLMs, the idea of instruction tuning came. So basically giving your data set in like an instruction, and this resulted into a whole lot of language models, which are basically instruction fine-tuned language models. So from T5 we got Flan T5, and for Palm we got Flan Palm. So these are instruction tuned language models. And similarly, people did the same thing for LLVMs also, and people created visual instruction tuning data sets. And as the idea of instruction tuning went into LLVM space, the whole idea was that they just kept on increasing the size of the model, and this completely overlooked the detailed and the comprehensive real world scene understanding that is available from CV models, which like people have worked quite a lot over the last decades. And the another concept that they use here is the MOE, mixture of expert concept, and the concept relates to the idea that where separate networks called experts handle different segments of the input space, and each segment is guided to relevant experts by a gating network. So in an MOE model, typically how it is implemented, let's say in our attention block, the feed forward layers. Traditionally, we would have, let's say, one single feed forward network, right? Like it'll be one network which basically let's say converts the input from dimension 4096 to, let's say, 12,000, and changes it back from 12,000 to 4096. Traditionally, we used to have one single layer of this. In a mixture of experts, there are, let's say, 8 of these. And what happens is that after the self attention, or let's say cross attention, the input is then sent to a gating mechanism which decides which of these expert the inputs should go to. So what ends up happening is that let's say these 8 feed forward layers, one of them becomes, not just one of them, like a couple of them would become good in a particular type of task, and some other will get better in different types of tasks. So basically what ends up happening is that these experts handle different segments of the input space, and and the gating mechanism decides which feed forward layer to pass it to. Now this happens in each encoder or decoder block, and let's say if you have 64 of these, then you will have 64 of these net expert layers. And let's say if you had in each layer you had 8 experts, so there you will have 64 into 8 experts in total within your model. And yeah, as the Mistral model 7 into 8 7B instruct model, you can see how good. I mean, I have also experimented with it. It is really good, especially for instruction-based tasks. So, and it is also rumored that GPT-4 is also a MOE model. So yeah, there's something here which is interesting, and yeah, it's worth exploring. Yeah. So let's now discuss the model architecture for the MoAI. So they have done a very terrible job of their explaining their model architecture using image, but uh, there are three components. So you can imagine this part as the vision part. This is the language part, and this is the auxiliary CV model part, the MoAI compressor. And all these three features, they are later added to the MOI mixer. MOI mixer is basically nothing like, you can think of it like a normal transformer architecture. So each layer in that architecture gets three features as an input. Um, so let's say if you have an image, like they have some image of a truck here, so that the image features will go through the vision component and an MLP component, which we will discuss later. And the same image will be passed to CV models, which by a process of verbalization, we will discuss that. It converts them to auxiliary visual information, and later on, these features are passed as auxiliary features to the model. Yeah, again, it will become more clear when we discuss the discuss the paper more. Yeah, so the vision and language backbone. So this part of the model is basically clip L by 14. This is the vision encoder here, which gives these features, the image features. The MLM utilized in this model is based on the intern LM7B. So this part here is the intern LM7B. And now let's talk in more detail about the MOI compressor. So Um, so yeah, so what happens is that hmm, in the MOII compressor, they are using four external computer vision models. One for panoptic segmentation, second one for open world object detection, third one from scene graph generation, and the last one OCR. But these models are basically prediction models, right? So how do we convert whatever they output into into text also, because that is what our model will be able to process. So they do that by this process called verbalization, and which is quite easy to understand. So let's say the image is passed to the panoptic segmentation part of the model, and it will result something like this. Like there is a sky in these bounding box coordinates, and there's a person, there's a truck, there's a grass. So they convert this output into text like this. So the image includes bounding box coordinates and their objects. So this is the bounding box coordinates, and the object there is sky. Similarly, for open world object detection, they identify the objects like a flag, flagpole, statue, clock, and they convert the results into text just like this. And scene graph generation, they would convert this into, let's say the image includes a relationship between objects. Like this will be a generic statement, which will be there for each and every prediction. And then the answer predicted from the model will be converted to something like person is carrying backpack and person is on motorcycle. And similarly for OCR, they will tell what all text is present in the image. And what happens is that all these texts are later converted into the word embedding part. They will generate the word embedding, which will be the word embedding will be calculated from the MLM backbone. They'll use the word embedding model that is used there, and they will convert them into features like this. So APS is the auxiliary features from panoptic segmentation. AOWOD is from auxiliary features from open world object detection, and similarly for SGG and AOCR. So in MOI compressor, what happens is the final auxiliary features are basically what they do is they concatenate all these features APS till AOCR, and A input are their learnable features here, which are learnable features because anything that is here, a part present here, that cannot be trained because these we are not here to fine tune these models. We are just using their results for our inference. So, but this process has to be a little bit learnable, right? Because we have to be able to understand how to convert the information which is present in these tokens to a representation which can be leveraged by a model. So the A input is basically that part of the model which is learnable, and it is passed through the MOI compressor, and we get the A, which are the auxiliary features referred here. You see these blocks that are sent to the MOI mixer. So that was MoAI compressor, basically the part of the model which compresses the information from the external models to something which the rest of the model can leverage. So now an MOI mixer is basically present in each MLM layer of the model. So this whole architecture is like a general transformer architecture. So what happens is, let's say if you have 10 layers, so in each layer there will be an MOI mixer. What is that? We will discuss shortly. And this mixing of these three different features, the vision features, the auxiliary features, and the language features, is happening in each and every single block and each and every single layer of that model. So the input to an MOI mixer is the auxiliary features, which are coming from here, these, and the visual features that is coming from the clip model, and the language features, which are coming from the instruct what was that in? Yeah, intern LM7B model. Yeah. So traditionally, what would happen in an MLM layer, multimodal language model layer, is that the input, the image features and the language features, which are passed on to the next layer, which are denoted by the IL plus one and capital LL plus one, is basically a transformer decoder block at the L layer, which gets the input of the image features at L layer and the language features at L layer. So basically, it's very simple. In a simple language, it is like a normal transformer block. Basically, in large language models, this input will just be the embeddings for text. But in a multimodal language model, both the image features and the language features are passed into each and every layer. So what change the authors have suggested is that instead of directly the transformer decoder layer, which is represented by trans deck here, first the image features and the language features are passed to the MOI mixer along with the auxiliary features. When that is through that, this MOAI mixer outputs the image features and the language features, which are now learned over using self-attention and cross-attention between these three features. So it becomes a bit confusing right now, but it will get clear in just a few more minutes. So now these image and language features are then passed through the traditional transformer decoder block, and that does the normal self-attention between image and language features. So now, let's say if our model had two layers, okay, for simplicity, what would happen is that in the first layer, first the inputs, the image and the language inputs would be passed to the MoAI mixer along with the auxiliary features. It would now output the image and language features which have taken some sort of information from the auxiliary features. And then these outputs are then passed to the decoder layer. So traditionally, if we had two layers for our model, now it would effectively be four layers because each layer is then converted into two steps like this. So the I I cap and L cap here basically are combination of six experts, which are I auxiliary, I lang, and I self. So I auxiliary basically refers to the cross attention of the image features with the auxiliary features. I lang refers to the cross attention features of the visual features with the language features. And I self is basically self attention of the image features with themselves. Similarly, we do it for all the language features also. So L aux is basically cross attention features of the language features with the auxiliary features. L image are the cross attention features of the language features with the image features. And L self are the self attention features of the language features with themselves. And these six are the experts that we are talking about, the mixture of intelligence, MoAI. So the mixture of an expert part are these six experts. Now, how they are experts? Because each of these experts is learning information from different sources. So traditionally, what would have happened is like, yeah, no. So these experts are taking information from different parts of the input and by different combinations of these inputs. And at runtime, basically a gating mechanism will select two of these models, two of these experts to use the information from them. So, yeah, any questions till now?
Why is it choosing two? That seems like an arbitrary one.
It is choosing what?
Why did you say it's? You said it's choosing two models to use. Like why two?
Because that is the whole idea of mixture of experts, right? You don't pass the all the inputs through all the experts. Yeah. So the idea is instead of having, so for example, let's say if we have a visual, we have an image of a PDF, and um, we don't have much information about what is present in the PDF, right? For an example, we don't have any related text, but what we can leverage is the OCR of that PDF page. And so what would happen is that the image auxiliary features would be able to do a better job of giving valuable information to the model rather than the L self, which is the language, the self attention features of the language features with themselves. So the idea is that these, depending on what kind of input you have, right? Let's say you get some valuable information from the scene graph generation model, right? So leveraging that at runtime, and so that is why so we generally select two out of, let's say, eight, because that gives us the benefit of having computationally more parameters that we can learn from, yet we have lesser number of parameters to do an inference from. Okay, so instead of having all the eight in parallel and doing inference of them, we typically train them in a way that at any single time we can just use two of them.
Got it. Okay.
Yeah.
Yes.
So these these are the 6 experts that are there present in each layer of the model of the MLM layer of the MLM, multilingual language model. And this notation is a bit confusing, but it tells what we just discussed right now. So in addition to MOE concept, they are also leveraging LoRa. LoRa we have discussed in one of our meetings earlier. So LoRa is basically instead of fine tuning your entire set of parameters, what we do is we construct, we convert or we reduce the number of training parameters by converting the matrices into smaller versions of them, basically by reducing the number of let's say if we had a matrix that converts from 4096 to 1024. What we can do if we can convert these operations into two matrices. We convert 4096 to 512 dimension and then 512 to 1024. When we do this, the number of operations and the number of parameters that we need to fine tune reduces. And that is the idea behind LoRa, to reduce the computational burden. So they apply LoRa for the linear projection layer in the multi-headed attention module. So basically the matrix that converts the query key value features into their respective dimensions. So basically if the original matrix was D into D, they would convert them into two matrices, D into R, and then the second matrix will be R into D. So this reduces the number of parameters that they have to train. So they do this for all the multi-headed attention modules for in the linear projection layer. And yeah, so while training, because still not the gating mechanism, which we'll discuss in just a minute. At the beginning of the training, what they're doing is they are sampling the they are sampling the from these 6 experts. They are sampling randomly 2 for the image features. The output of the image features that will be propagated to the next layer will be randomly chosen between I auxiliary, I language, and I self. And similarly, it will be randomly chosen for language features. It will be randomly chosen between these 3. So the reason behind doing this is that when you're setting up your model, the model is able, all these experts, they are able to learn valuable or learn important features from the inputs that they're getting, and they're useful in the later step of the training. And once they have done the first training part, basically they are fine tuning the entire model to a visual instruction tuning dataset. In the second part, they introduce the gating networks. Now, why they select 2 of them, it will become clear how they are doing it. So in Mistral paper, there is a single gating network which selects between, let's say if you have 8 experts, it will give you softmax values, sort of like softmax values for the weightage for each network, for each of the 8 experts. And there we take the top 2 values of them. So what happens is, let's say let's begin with the Mistral example, then it will become clear how what is happening here. In Mistral paper, if you have 8 experts, you select 2 of them. Let's say the weightage that those 2 experts got was 0.9 and 0.1. Now that input will be passed to those experts, and whatever output that you get from them, their values will be multiplied by 0.9 and 0.1 and added back together to get the values that will be passed or propagated further. So similarly, what is happening here is, like, there is a gating network for the image features, there is a gating network for the language features, and this gating network for the image feature will select which one of these experts to select from. So let's say if it gave W self zero point 0.8 and W lang 0.2. So whatever value that we got from I self will be multiplied by zero point 0.8, and whatever value we got for I lang will be multiplied by zero point 0.2, and they will be added together, and this would be sent as the image features to the next layer in the architecture. And so at any one time, one of these will be selected. In implementation, it's like the weightage won't really be like zero point 0.9 and zero point 0.1. They will select like one of them, top of them. And yeah, so the W gating matrices are very simple. They have the dimension of R into D into 3, and D is the embedding dimension that is there in the model. And yeah, so that's about the architecture of the model. And quickly covering the experiment. So here they mention what all models they have used for, let's say for panoptic segmentation, they've used mask to former. For OCR, they've used pedal OCR. And yeah, so these models are not fine-tuned. They are just their inference is just used as training features for the MoAI model. So evaluation of the zero shot performance. Here you can see the different zero shot performance of the model on different data sets. One interesting thing about the zero shot performance is that it is doing better zero shot performance than the models which are comparatively much bigger than the model MoAI model that we discussed here. So let's say we have a very huge LLVM model. It is giving comparatively similar or better performances to them by having lesser number of training parameters, which is always a good sign to have. And yeah, yeah, we just discussed this. And another interesting thing is that MOI performs well even on hallucination zero shot datasets. So since its understanding is much more grounded into models which are really good at their job, it is much more prone to hallucinations also. And that is another very good feature about this. And here you can see the performance of um, performance of MOI model compared to other models. So other closed source LLVMs like GPT-4 Vision also is mentioned here. So this part here shows the number of parameters, and you can see the accuracy of MOAI is even better than the GPT-4 Vision model, where whose number of parameters we really don't know. And on the MME dataset. And yeah, so that's from my side. That's
Wait,
all.
one question on the graph. Why is the MOI the same? Oh, MOI level 1 second. Okay, I see, I see. What is Pope? The one of the data
I,
sets?
I assume that's a dataset.
We got it.
Which one it is?
Interesting. Okay.